abbreviated as REF. So reduced echelon form is where you quite literally have the answers in the column that's to the right, so kind of the augmented matrix column to the right. Because if you have this matrix here, then x3 equals C, x2 would equal B, and x1 would equal A. So reduced echelon form, which is also called reduced row echelon form, you also will see it that way, or RREF. For short, that's when you use technology, that's how it is abbreviated, reduced row echelon form. It creates that 3x3 matrix that looks like that. Do you guys remember what we called this 3x3 matrix? Just the 3x3 part of it. This one in particular, 1 0 0 0 1 0. This is way back from freshman year. Yeah, this was actually the identity matrix. And so when you have the identity matrix here, that means that you have solved for A, B, and C. You have solved the matrix. Okay. Now, the form that I suggested you get it in is echelon form. And so that's why, right, when you were talking about just getting a row with 2 zeros, which works, but to get the triangle of zeros right here, you have what's called echelon form. And it's fairly straightforward to solve after you get it into echelon form, because all you have to do is divide C by I to get x3. And once you have x3, you can substitute in to get x2, and then same thing to get x1. So echelon form just requires a lot less work because getting these extra zeros in the matrices is tedious. So this we're going to solve by getting it into echelon form. So let's begin by writing this as a matrix. Okay, so one of the first things I'm going to do is switch some of my rows, and I'm going to take 2R2, 2R3 plus R2. So let me just do some of that. So I'll go R2 negative plus R3. 2R3. So adding, I get that. Sorry, this was positive. Yeah, so I'm not being super careful with my row operations there. I'm going to scale it so that's 0, 1, 1, 3, multiplying it by negative 1/5. And so I'm going to throw that. I could put that into either R1 and R2 since I've used both of them. I haven't used R1. So I'm actually going to flip this into R3. I'm going to put R1 into R2, and then I'm going to move R3 up to the top. Right, any questions so far? So right here, I'm going to do R2 minus 2R3. And I'll throw that into R3.
What happened to R2?
Into R2.
Switch back to that one. Switch R1 and R3, that's what we're going to do.
Yeah, so R1 went to R2. I replaced R2 with this. And then I moved R3 up to R1. So I did like probably 4 or 5 different elementary row operations here. Was that too much? I'm sorry. Other questions? All right, so it looks like we have, this is X1. X. Okay. Right here?
Yeah.
That is this. So I wanted to utilize the fact that R1 had a 0, so I did an interchange of rows so that I could use that to my advantage to get my triangle of zeros. I put the result from this elementary row operation in here, and I really hadn't yet used.
So you put in R1 and then you switch to
So I did an elementary row operation with R2 and R3, which means I could interchange this row with either R2 or R3. So I decided, because R2 had a 2, a 3, a 1, and a 5, I decided to switch it with that one. So this I interchanged with R2, and I actually put it in R3's row. So this went here, this went here, and then, let me use a different color. This one went up here. Right?
So I think yesterday you said that you should do the one that you haven't changed, like you should substitute for the one that you haven't really altered.
Yes.
Would it be incorrect then to substitute it into R3? Because you still get the same answer.
So no, at this point, it doesn't make a difference in solving, but it will make a difference later, because technically I'm doing something more than an elementary row operation. Because notice with this is a plus right here. I'm not keeping any one row the same here. I negativized one row, I multiplied one row by 3, so that's technically not an elementary row operation. Let's call it like a secondary row operation. I made that up, I don't know what it is. It's not illegal as long as I exchange it with another row, a row that I have used, either R2 or R3. However, do you guys remember determinants? Okay, so some of these row operations change the determinant of the coefficient matrix. Some of them do not. But this is not an elementary row operation, it's an elementary row operation asterisk. So if I'm worried about the determinant, I would have done R2 plus negative R3, negative 2R3, and then replaced it with R2, and done that as one elementary row operation.
So if it's perfectly in line with elementary operation, it won't change the determinant.
Some elementary row operations change the determinant, and some do not.
Okay.
And each elementary row operation changes it or doesn't change it in different ways. So when you do elementary row operations to a coefficient matrix, you have to keep track of what elementary row operations you have done and then change your determinant as you go. So when we're keeping track of determinants, we won't want to be this fast and loose with our elementary row operations. At this point, it does not matter because we're just accomplishing the goal of solving. Any other questions as to how I got this matrix right here? So at this point, looking at this matrix, I have that x3 would equal 2 because of this coefficient. Then I have 2x2 plus 3 times 2 equals 8. And so that means x2 would equal 1. And then looking at my top row, I'd have x1 minus 1 times 1 minus 2 times 2 would equal negative 5. And so that's x1 would be 0. So there is my solution. We can just kind of make sure it works in my matrix. So 1 and 2, that would give me 8. 0, 1, and 2, that does give me 5. 0, this would be negative 1, and negative 4, that does give me negative 5. Any questions on that? All right, so that's echelon form. Okay. So an expanded definition of echelon form using some more notation is that if you are in echelon form, any lead entry, and maybe I'll just kind of recopy this. So I had 1, negative 1, negative 2, negative 5, 2, 3, 8. What was after that? I don't know. Zero, 0, 1, 2, 2. Okay. So looking at this matrix, it's an echelon form. So echelon form isn't always going to be a perfect kind of diagonal. And that will happen if you don't have a unique solution or you have no solution. That can happen. And so an expanded view of echelon form is that any lead entry, and we have 3 lead entries here, 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 and here. So a lead entry is a non-zero leftmost entry. So if you look at each row, we have a lead entry. Under it, it will have zeros. That is echelon form. Right? So we could have had something like this. This is also echelon form. So you don't get that perfect diagonal, but notice it is echelon form. I have 2 lead entries, 2 leftmost non-zero entries, and then below these, notice I have zeros. Okay. Reduced echelon form would just mean I would take either of these and I would have, oh, they have to be 1s too. Sorry. So that's reduced echelon form. And if you have it in reduced echelon form, you're done. There's no solving to do after that. Reduced echelon form here would be 1, 0, 0, number, 0, 0, 1, number, and then zeros. All right. Now, a pivot position is a lead entry in a row. So everything that is highlighted in echelon form is a pivot. So in this case, for this matrix, I have 3 pivot positions. So therefore, I have 3 pivot columns. So pivot columns, column, column. Those are all pivot columns. In this particular, this particular matrix, I have 2 pivot columns. Okay, right there and right there, because I only have 2 pivot positions. Yes?
So this position is the same thing as the weight entry?
So it is, yes. And it is what is required to have a pivot row, or pivot column, sorry. Yes.
What's the pivot position again? Why is 1 and 3?
Okay, so it is the lead entry in a row. So if you have a matrix in echelon form, and we get rid or we discount the zeros, it's the first non-zero entry in the matrix.
And then the column is the one that contains
The pivot. Mm-hmm. Do you guys watch Friends? This is one of my favorite Friends episodes. I think I have to click it. No! It'll be worth it, I promise.
What episode is this one from?
I don't want to ruin it.
You know, Alex, you're just like a squirrel. This is what I've learned in my
Okay, the squirrel thing actually didn't that.
It's like kind of objectionable, but not that much.
Oh, let's just go to the internet.
No.
No, Perry Bart. Perry Bart. What is your name? Your name is Perry Bart.
Very Bart, B-L-A-R-T. I'm like 3 years old.
Oh, I'm excited. Dave said thank you for calling the Great Royale and today. He's the only one who can see that, right?
This might be weird. This might be a gap. All right. That's it. You're playing should always be in silence.
I don't know.
That's it's so
You should
I
not
didn't
say
know
that.
that.
Like, it's,
That's
I don't,
so
it's kind of funny, but it's not that funny. And then it's like super objectionable.
Okay, let me get the sound going.
It's
Oh,
not
I
like-
love this one.
It's not like work.
This is really cheap.
It's one of my favorites.
Yeah.
It's gonna be really loud, or not at all, one of the two.
The thing is not at all.
Wait, you never know. This could just be like a tour.
Here we go, pivot! 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 Shut up! Shut up! Shut up! Okay, I don't think it's gonna pivot anymore. You think?
I love that
The
one.
whole thing.
Yeah,
Oh,
it was worth it.
oh. What do I have to say? Ray, I'm so disappointed right now. That's like 76. What was it like one? It was like a million ceramic ones. Oh, wait, or clay ones, whatever. Another. It was like a million of them, okay? I understand that, but after certain.
Ray's playing to do not.
The only thing you can do to after a certain point, like especially nice things, is always like, I just should have loaded up more super.
Fatal mistake.
You shouldn't be losing anything on the floor by the time you do that part. I got the mob thing where it just like blows up all mobs. Yeah. Wait, is that past the zero? Or...
Okay, let's move along. So, what we're going to do, just so you know, your book goes through how to get it into echelon or reduced echelon form. I find the algorithm really hard to read, so I'm not going to go through it, but you can read it. All right, so take a look at this matrix.
This is just absolutely delicious.
Okay, well, we can lose the bottom.
Oh, maybe.
Okay, so the matrix has already been put into echelon form for you. You know that because all of the pivot columns are already followed by zeros below. And so you're in echelon form. Not reduced echelon form, but you are in echelon form, which means you don't have to do any reduced row operations.
Why is this in, I don't understand, so why it's in the form, it's for some,
Only the leading, so they're all on.
So here's x1, x2, x3, x4, and x5. And then we have our what that equals. And so it's always easier to solve if you work from the bottom up. So we know that x5 is going to equal 0.
Why do we know that?
Oh, that one, yeah. Got it.
Working our way to the second row, we know that x2 plus 4x3 minus x4 equals 6. And the top row, we know that x1 minus 5x3 equals 3. I don't have to put in minus 8x5 because x5 equals 0.
You have to make a whole new matrix to solve this.
You do not. Okay, so how many variables do we have?
Oh yeah, we have 3 unique reverse.
So we have 5 variables,
Well, one of them's 0.
but we have 5. We know that one is 0, but it still is a variable. Okay, we can call that an unknown. Let's call it a known. x5 is 0. So we have 5 variables. How many equations do we have that are actual viable equations? We have 3. Okay, this tells us something. It defines one of our variables to be 0. So we have 5 variables and 3 viable equations. So if we have 5 variables and 3 viable, I should probably, let me use this word, dependent. Let me use this word, independent. This will become much more valid and much more useful a word later, but we have 3 independent equations. So if you have 5 variables and 3 independent equations, can we get a unique solution? No. So because we have 5 variables and 3 independent equations, let me get a noun for that, what we're going to need then are 2 what are called free variables. In other words, our answer is going to have 2 variables that can be any number. They can vary. And so, obviously, 5 is not going to be one of them. x5 is 0. That is not free to be anything else. But you can pick what your free variables are. So if we look, we have 5 variables, 3 independent equations. 5 minus 3 is 2. So that's the 2 free variables. Okay. x1, you have an equation of x1 in terms of x3. You have an equation for x2 in terms of x3 and x4. So what do you think it makes sense to have as your free variables? Yes. X3 and x4. Good. So x3 and x4 are free variables. They can be anything they want. And so we're going to define all the variables in terms of either what they are or in terms of x3 and x4. Yes?
I mean, so it doesn't have to be x3 and x4, though, right? You can also have like x3 and x2.
It can be x3 and x2. Yes, we could have done that. So x1 equals 5x3 plus 3. x2 equals negative 4x3 plus x4 minus 6. x3 is free. So a lot of times we'll just write x3 equals itself, saying it can be whatever you want it to be. x4 equals itself, and x5 is 0. Yes?
I think it's plus 6.
Thank you. Ben?
Could you just define what a free variable is?
So that means x3 and x4 can be any real number. And then x1 and x2 are dependent on what x3 and x4 are. So, for example, if we choose, let's say, x3 equals 1 and x4 equals 2, choose any number, any real number to be those, then we can find x1 and x2. That will satisfy this system. Okay? So this is a way to define, instead of just saying there's an infinite number of answers, that's true, but this is what they are, okay? It's not any 5 numbers. It's any 5 numbers that meet these requirements, where you can pick any 2 numbers for x3 and x4. x1 and x2 are dependent on those, and then x5 is 0. Yes?
So free variables are when you take a variable and treat it like a constant?
No, it's any number. I'm just saying, for example, you could choose that as your number. And then if you chose x3 to be 1 and x4 to be 2, then you would know x1 would equal 5, x3 would equal 8, x2 would equal negative 4, negative 2 would equal 4, and x5 would equal 0.
In terms of the equations, they're like essentially constants for this solve.
Okay, so think of this in terms of if this were 2 planes intersecting. I know it's not because there's 5 variables. But if these were 2 planes intersecting, this would be like writing the equation of the line where all 3 planes intersected. So it truly varies. They can be any real number, and then the other ones are dependent on it. I'm just picking, for example, if you chose those 2 real numbers, this would then be the ordered quadruple that would be produced based on that.
So it's like saying in terms of x3.
Yes, yes, but it is any real number for those 2. Yes.
Sorry, can we go through how, like, we picked x3 and x4 again? I
So-
understand x3 since it's in both.
Okay, so the reason I picked x3 and x4 is because it was, first off, it was, I could write x2 in terms of both of those. I could have also picked x2 as a free variable and written x4 in terms of x2. So you pick 2 that you can write, well, in this case 2, because there are 2 free variables, that you can write all the other variables in terms of. So there are multiple answers for the way you can write your solution, multiple solutions. but X3 you pretty much have to because it's present in both of these. I'm trying to think, could you have done X1?
I don't think so.
You could have done X1 and X1.
X1 and X4, and then you have to like plug in to find the others. You can do that. But I just looked, I'm like, oh, I can just write X2 in terms of these two. I saw X2 and it was first, so I put those second and third. Now, you can write this also parametrically. Do you guys remember parametric equations?
Yes.
Okay, so we can say that X3 equals S and X4 equals T. And then X1 equals 5S, plus 3. I should make that look more like a 5. 5S plus 3. X2 would equal negative 4S plus T plus 6. X3 equals S. X4 equals T. And X5 equals 0. And then we could even take it a step further and write that in vector form where, if we wanted, okay, so that's me writing this in terms of vectors. So here are the constants, 3, 6, 0, 0, 0. Here are all the coefficients of S if I pluck them off. And here are all the coefficients of T. All right, because remember when we read how interrelated vectors were with matrices? This is one of those examples. We have no time. Those are in your book if you want to look at them. But here's your assignment.